Yes, is chapter 6. We'll do 7 next week. Okay, so guys, let's remember what these letters stand for. Hey, listen up, please. Let's go. These letters, P stands for population. I tried to choose smart choices for my letters here. So P stands for population, and that would be the population that has heard the rumor, the population that's gotten sick, the population that has the idea, like the size of the population, depending on what we're measuring. P stands for population, K is a constant, and M is the carrying capacity. I chose the letter M because M maybe maximum, right? Maximum would be associated with carrying capacity. So maybe just hopefully a good mnemonic device there. Exponential growth, this is what we talked about last 2 days ago. For exponential growth, the rate of growth is proportional to what? You can say it in 3 words. For exponential growth, the rate of growth is proportional to the blank, blank, blank. No. With exponential growth, the more that's there, the faster it grows. To the amount that's present. Sure, population. So you could say rate of growth is proportional to the amount present. Or you could say population. Amount present. Logistic growth, a little more complicated. You can see it represented in the differential equation above. If you just did this, if you crossed out all the stuff that I'm crossing out right now, if you cross that out, is that not, what's left over there, isn't that the differential equation for exponential growth? dp dt equals kp. Rate of change is proportional to the population, the amount that's there. So then when you get rid of that and you say, all right, well then what does that mean? So we got to say this. It doesn't flow off the tongue as easily as the other one. You'd say the rate of growth is proportional to the product of the amount present, which is the P there, the population. Product of the amount, present times, how would you guys describe 1 minus P over M? P stands for the population that's gotten sick, and M is the carrying capacity. Like what is 1 minus P over M? Okay, so you're referencing the sick. So it's, okay, and I like that. I think that's pretty good. He said the percent well, right? It's actually, if we're going to use the sick paradigm, then that's pretty good. 1 minus P over, let's think about it like this. This might help you guys develop this a little bit better. What's the maximum value for P? M. And as P gets closer and closer to M, 1 minus P over M is getting closer to what? 0, right? Because it would be getting closer to 1 minus 1. And so what I said was if P is the population that's sick, Johnny said then 1 minus P over M would be like the percent that's not sick, right? So you could say it's the product of the amount present times the amount not present. You could, not amount, sorry. I wanted to say percent. Times the percent not present. So is that percent not present or that percent not sick, to kind of parody what we did a second ago, gets closer and closer to the carrying capacities, whatever that level is, well, that 1 minus P over M is heading towards 0. And you see how that's what causes the dp dt to flatten off and have no growth? Think of it like this. As P gets close to M, 1 minus P over M gets close to 0, and dp dt would get close to 0, right? Hence the whole flattening off as we get closer to the carrying capacity population. Anyways. This right here, this is one form of a differential equation for logistic growth. There's one other form. It's pretty easy to go between the two, and I think you would be expected to be able to go between the two. It involves basically like, can you factor out a 500? and still recognize the pattern. We'll practice that a little bit, but I just want to let you know there is another form of that. We'll get to that. But here's the bottom line. If you see a differential equation like that, and it's got to be just like that. So like if P were something different, like if this, if that instead of a P that was a T, then it's not logistic growth, right? If instead of a P right here, it was something else, maybe a whole other variable, maybe it was an M or a T or anything other than a P, it's not logistic growth. It's got to be exactly that. So you would be forgiven perhaps, especially right now, if you saw something like this where it said dy dt equals k times y times 1 minus, t over m, or t over y, excuse me. If you saw something like that, do you see how that looks a lot like logistic growth? But it's not, because instead of the t, it would need to be a y. Instead of a y down below, it need to be like an m or a number or something, right? So it looks really close, but those two things are kind of flipped around, and the t really doesn't even belong in there anyways. Do you see what I'm saying? So please don't just look at the structure of it. You need to pay careful attention to what the variables are and where they are, and is it really this or is it not? Okay, it's possible for something to look close, but it's not actually yet. All right, so the bottom line is, if you do recognize that you've got logistic growth, maybe a differential equation for logistic growth, here's what you can do. You do not, and I don't think you'll ever be directly required to prove this. I know I have never seen it done like on an AP test. I've never assessed it directly. If there's a differential equation, there's probably a solution for it, and the solution is down below. So if you understand that differential equation for exponential growth, you're allowed to essentially jump to the solution curve without showing all the steps. That makes sense? And so the solution for dB dt equals kp times 1 minus p over m is m over p equals m over 1 plus ce to the negative kt. And again, a little device here to help you with this is mice minus Katie. So let me scroll a little bit so you can kind of see how that's supposed to work. And there, of course, is your picture that hopefully will stick this in your mind. You got some mice crawling around in the sawdust, eating things, dirty, icky little mice, and then Katy Perry with some trophies and purple hair. So here it is. Maybe it's obvious, maybe it's not. So here's mice. I'll color it in green. And obviously minus is in red. And in purple, there's Katie. Right? You see mice minus Katie? You know, hardly creative, but whatever. Just if that's enough to help you. There are other things. I've seen one called lice minus licked. Some other teacher came up with that. It was lice, and it was this cow with its tongue. They used L for carrying capacity. It's gross. I like this better.
Is the C the constant of integration?
Say again?
What is the C?
So yeah, C is going to come out if you do your actual integrals and such. Yep. Yeah. So C and K they're both constants, but they're different constants, most likely. They're definitely not the same thing for sure. So then you'll have boundary conditions, like you'll have an initial condition, or you'll have like, hey, after so long, 10 people were sick or whatever. You'll get some boundary conditions to help you find the C and the K in some form or another. Okay, questions, concerns at all? Okay, so let's see here. Let's look at least one of these here. Let's just kind of see what it looks like, and we'll go from there. Yeah, this will be good. Okay, grizzly bears. Example number 1. I think there's just 2 examples, right? Yeah. Okay, so let's do grizzly bears. We can save the other one for tomorrow. Okay, here we go. 10 grizzly bears were introduced to a national park 10 years ago. There are 23 bears in the park at present time. The park can support a maximum of 100 bears. Yeah, assuming a logistic growth model, when will the bear population reach 50? So first of all, does it make sense to you that someone would assume a logistic growth model here? Aren't there environmental factors that would basically restrict the growth of the bears? Even if it was Yellowstone, which is a gigantic national park, if you've ever been there, it's huge. If you're to say, hey, you know what, I think it's going to eventually have like 50 billion bears, You got to realize, I mean, right. But if it was exponential or geometric growth, wouldn't that be the case pretty darn soon? It wouldn't take that many years for there to be like 50 billion bears in there. It really wouldn't. So we're going to assume that it's logistic, not exponential. That is an assumption. Okay, so can anybody identify any important stuff coming out of this? M is 100, right? That's the carrying capacity. I agree. I think that's a good thing to notice. So we could say M is 100. Okay. Anything else? So, and of course, T equals 50. It says when. So what kind of a question is when? When is associated with time. There we go. And it's not when is time 50. It's when will P be 50. Yeah, so we could say T equals, we don't know when the population of bears is 50. Something like that. So we've identified what we're trying to find. We've identified the carrying capacity. Maybe now would be a good time to get our not exponential, I keep saying that, get our logistic growth equation up there. So I'm going to write it down. This is where your mice minus Katie comes into play. You'd say population of the bears is equal to mice. See it? Minus Katie. Any questions?
What is C again?
So C would be the constant of integration that came out when you actually solved that differential equation we looked at earlier.
Gotcha.
So it's really not that hard of a differential equation to solve. It involves some partial fraction decomp. It's a little bit awkward because everything's variables. So you got to think, all right, well, when I make P this, what's going to happen? It's a little awkward, so I'd rather not use class time to do it, but that's where it comes from.
Okay.
Okay, so then you guys mentioned that M is 100, and so I think we can fill that in. I've got 1 plus CE to the negative KT still. And all this is going to come down to, for me to be able to answer the question that's asked, I got to figure out what the C is, and I got to figure out what the K is. So any ideas on what I could do to do that? Is C equal to 3?
23.
Why would you assume that?
Because in the other one, it was like C is your initial value.
Okay, let's talk about that. Why are you thinking that 23 is an initial value?
Just because it looks like it from the other one.
Well, I think it's... I think we have to be careful with this. 23 is a number of bears, but it says there are 23 bears at present time. You think, okay, so maybe you think that is the initial, but then when you look at the first sentence, it says 10 grizzly bears were introduced 10 years ago. So 10 years ago was actually our start, right? And so when T is 0, P is 10. It's going to be tempting to say, hey, that means C is 10. Let's find out. So P is 10 when T is 0. So it'd be 100 over 1 plus CE to the 0, right? Because 0 times K would just be 0. So then, of course, e to the 0 is 1. So this would go to, over here, 10 equals 100 over 1 plus c. What would you guys do with this? Yeah, multiply by, okay, there we go. So 10 plus 10c equals 100. So you subtract 10, you get 90. You divide by 10, and you get 9. Interesting. So it would have been tempting to just say, hey, automatically c is 10. It doesn't work quite that way here with logistic growth. C was 9. So then that means I've got P equals 100 over 1 plus 9e to the negative kt. The last piece I've got to find before I can finish this is the k value. Any suggestions on that? Yes, Liz?
You said like 23 bears.
So 23 bears when...
Equals 10.
There you go. So we could say, this might be a calculator moment here, 23 equals 100 over 1 plus 9e to the negative 10k. We're going to have to do a little algebraic gymnastics here. You can swap the denominator with the 23, subtract 1, divide by 9, natural log of both sides, then divide by negative 10. I'm hoping that you, based on all the work we do with exponentials, you can whip through that really quick. Anybody have the k value?
0.09889.
You guys agree with Josh's number? 0.09889. Okay. Cool. All right, so then once we use the boundary conditions to find the c and the k, we have our complete logistic growth model. So P equals 100 over 1 plus 9e to the negative 0.09889t. And finally, we can ask the question, when, so it's a time, when will the bear population reach 50? So where do I put the 50? Yeah, I put it in there for P. So I can say 50 equals 100 over that denominator. And we can use some nice algebraic solving techniques. So let's see, it'd be 2, so 1. So 1/9 equals e to that number. You do ln, you divide by that negative number. I'm guessing just by body language, some of you have answered this, yes? T equals what?
42.219.
Agreed?
Yeah.
We all trust in Josh? Or we've done these numbers? Okay.
Josh, we tried.
Usually that's a pretty good bet. I mean, he's not perfect, but usually he gets it right,
Pretty
right?
close.
And so,
Expert.
okay. Okay, so what do you guys think? Questions, concerns, comments, thoughts? You okay with logistic growth?
Concerned about the bear population 100 years from now.
Yeah. 22 years.
Bears.
Jaden.
So on a test, will it say like that we should use the logistic growth model, like this question, or will we just infer it?
It depends on the question. So it depends on what the question is trying to get you to do. There will be I can definitely think of times where I've seen lots of times, really, where it'll say, hey, the following is a logistic growth model or something like that, right? And other times it'll just give you like a differential equation and expect you to notice it. Or there are certainly times where I've seen on AP tests where it'll be like a multiple choice and it'll say, which of the following represents logistic growth? A, B, C, D, E, whatever. And then you got to pick the one that actually fits with the logistic data that was given to you. So two very different questions, right? One is like assuming that you know what logistic is all about, and the other one is like, do you even know what logistic looks like? So you kind of have to know both sides. Yeah. Okay, so we'll practice that some more tomorrow. Tomorrow we'll also touch on, you guys remember when we did that first order linear differential equation? We'll do one or two of those tomorrow too. So
What is the first order linear differential?
we did it when we were doing slope field stuff.
Oh, okay, yeah.
We'll do another one or
So
two of
like
those
1
tomorrow.
minus x equals 2y dx.
Yeah. All right, guys. Let me get your tests out to you.